Hi everyone, and welcome back to Big Picture Technology and Science. Today we'll solve a simple exercise of a parallel circuit, and as always we'll start with a 60 seconds review of the theory and the formulas. So here you have a simple parallel circuit with two branches. These two branches are connected in parallel because they're both connected to the same points, to point A and B. And in this case, the two branches are connected in parallel to the voltage source itself. So let's look at how voltage, current, and equivalent resistance behave in a parallel circuit. So in a parallel circuit, the voltage over all branches is equal. In this case, U1 equals U2, and in this specific case, they're both equal to the battery's voltage. The current behaves differently. Current is distributed in parallel branches, and therefore the total current divides between the two branches. Therefore, I total equals I1 plus I2. And we have simple formulas that tell us how exactly is the current distributed, how much goes into each branch, and these are the formulas. I1, the current that goes into branch 1, equals the total current times R2, that's the resistance in the other branch, divided by the sum of the two resistances. And what about equivalent resistance? Well, the equivalent resistance general formula is this: 1 over the equivalent resistance equals 1 over R1 plus 1 over R2. But the more useful formula, as you'll see, is this one. The equivalent resistance of a parallel circuit equals the product of the two resistances divided by their sum. And this becomes even simpler when two resistances are equal. Let's assume both are equal R, then the equivalent resistance becomes R divided by 2. Okay, let's start by calculating the current within the two branches. There are two approaches that one can take here. I'll show you both of them. The first approach, I call it the Ohm's law approach. Sorry about that. Ohm's law. You probably remember Ohm's law. Ohm's law is this: U equals I times R, and if you can write it also I equals U divided by R. And that means that if you are looking for the current between 2 points on the circuit, all you need is the voltage between these 2 points, the resistance between the 2 points, and you can get the current. And how does this apply to our example here? Well, you remember that the voltage over branches in a parallel circuit are always equal. And in this case, they're equal to the battery's voltage, which is 10 volts. Therefore, we can write that U1 equals 10 volts. And also U2 equals 10 volts, because they're both connected to the same 2 points and they're in parallel to the battery. So now calculating the current within the two branches becomes simple, because we have both the voltage and the resistance within each branch, and therefore I1 is U1 divided by R1, and U1, as we said, is 10 volts, R1 is 3 kilo ohms, and therefore the current within this branch I1 is 3 1/3, and it's milliamps because it's volts and kilo ohms. I2, the same way, is U2 divided by R2, that is 10 volts, same voltage, divided by 7 kilo ohm, which gives us 1 3/7, and again milliamps. And for calculating the equivalent resistance of these two branches in parallel, we'll use our simplified formula, and this becomes our parallel equals the product of the two resistors, 3 times 7, divided by their sum, This becomes 21 over 10, and that's 2 and 1 kilo ohm. I want to quickly show you a different approach to solving this exercise. So let's take a different approach. That approach would start by calculating the equivalent resistance, and we won't do it again. We know that the equivalent resistance is 2 and 1/10 of a kilo ohm, and that is 2.1 kilo ohm. We need to understand once we have the equivalent resistance, it means that we can replace our original circuit with a very simple one which has just one resistor, one that would look like this. Just a voltage source and one resistor that equals the equivalent resistor, the resistance that we have just calculated. Our circuit becomes something like this. And this simple circuit, in this simple circuit we can very easily calculate the total current, right? Because we have just a voltage source and one resistor, and the total current, I total, becomes 10 divided by 2.1, and that equals 4.76 milliamps. So now we know what the total current in the original circuit was. It's the same total current. I'll write it down here. And now we can use the formulas of current distribution in a parallel circuit to calculate the current within each of the branches. And I1 would be I total times R2 divided by R1 plus R2. That 4.76 times 7, that's R2, divided by R1 plus R2, that's 10, and that would equal 3.33 milliamps. We'll calculate I2 the exact same way. I2, that would be I total times R1 divided by R1 plus R2, that's 10. That equals 1.428 milliamps, and the results, not surprisingly, are the same as the previous results using our first approach. And finally, some of you might have noticed it, the last calculation of I2 is somewhat redundant, because once we have the I total and I1, we could have calculated I2, because we remember that the total current in a parallel circuit divides between the branches. So if we know the total current and I1, we could subtract one from the other and get I2. So let's do that and make sure that the results remain the same. I2 would have been I total minus I1, that is 4.76 minus 3.33, and that gives us 1.43 milliamps, which is exactly the same result, accounting for the small rounding inaccuracies. That's it. These are the two approaches for solving a parallel circuit. Thanks for watching.